All right, so today we're going to be discussing the synthesis and analysis of aspirin. We're going to briefly look at the video very lightly just to show you some key ideas that I'd like to touch on. And then, of course, we're going to be reviewing the lab manual like we usually do. Then make sure that all quizzes that they needed to be completed, because everything, like I said, is going to be graded and due to the university by Monday. So everything's finalized over the weekend. Finish everything out if you haven't. And then when you're done, make sure to post your lab notebook into here, and we'll discuss the data at the end of this class period. So I'm going to stop sharing for half a second, switch over to my lab manual. Okay, and so like usual, these are more short because a lot of it's just heavy mechanism. So today's class period, of course, is going to be short, but we're going to go forward and do a overview of this. We're going to likely look at the video, look at the mechanism, and then I will tackle any extraneous questions that you'll have afterwards. So firstly, we're going to discuss acetylsalicylic acid, which is the name for aspirin today, and it's a very straightforward reaction that will include the reaction between salicylic acid, which will be the phenolic group that'll be reacting with this acetic anhydride and through a substitution reaction, and it can also be known as an acylation reaction. And the big portion here is going to be the mechanism pathway of which that the acetic anhydride can go forward to replace the proton and have us as a side group product for acetic acid. So within the experiment, don't forget to go through and have the melting machine as a method of your machines. And secondly, to have your spectrophotometer in order to go forward and validate the testing of absorbance of salicylic acid impurity after it's been complexed with iron 3 from the iron 3 nitrate solution. And if you need any sort of review of absorbance and Beers-Lambert law, make sure to review my other videos that regarding I'm actually unsure that if I have an absorbance video for this, but I would recommend to go forward to look at UV visible analysis and to review Beers-Lambert law. Beers-Lambert law will be the way that you will be able to back calculate the relative concentration, because the absorbance, if you measure it, and it's not very easily seen here, but hopefully in the video it will be able to be seen, is that the absorbance of salicylic acid will be present at a different wavelength than the presence of acetylsalicylic acid. And so when we calculate the absorbance of it, you can utilize Beers-Lambert law to back calculate your concentration. And once you have your concentration of salicylic acid, then you can calculate how much of your starting material is left in the product, and then how much of your product is there as a total, because it's going to be a crude mixture of your product. And then a relative percentage of that will be your starting material of salicylic acid. So of course, go through here and make sure to look through your full portion, and then I can list it out here, some of the things. So salicylic acid will be a organic waste. Acetic anhydride, that will be considered organic as well. Effectively, everything here can be organic, so that way it's easier for you. And then phosphoric acid can be considered aqueous waste. That one specifically, you would want to have an aqueous waste. Then down here, you have your glassware, and it's also listed throughout the video to review the full video that we'll be seeing, and that I recommend everyone to watch through if you need to get out every single item. Another portion that would be a machine here would be this hot plate / stirrer. And then going down into here, let me check to see if there's any other additional machines you need to worry about. Make sure to list out all glassware for vacuum filtration, with including the sizes there. And then, let me check here for one moment. Just make sure to have this adequately listed out as usual. And then the data table will be analyzed, and we'll look at the data here at the end of the lesson as well after we review the video. And then don't forget to perform your data analysis with regards to the given data as well. And so here would be an absorbance versus concentration of aspirin situation here. And this given multiplier next to the X would actually be the given concentration. So with that given information, take that data and then interpret it, back calculate it in order to take the concentration and then remove that from your final product, and then you'll have, you know, your relative quantity of salicylic acid, relative quantity of acetylsalicylic acid. You subtract them, and then you actually have a full percent yield. And so this is a good practice to know from utilizing this within lab, because then that way, if you did have a crude mixture, you could go forward, take it onto your spectrophotometer, and then check how much of your actual product you got, and then how much of starting material was left on the side. So I'm going to stop the share on that portion and then take it over here to our video for the synthesis, and we're going to briefly jump through it. And I'm going to save most of the other extraneous information, you know, the weighing and all this stuff on the side, so that way that you can review it on your time. But what I really wanted to show here, and is very important, is going to be the reaction mechanism, okay? So firstly, we're going to see that the oxygen of the carbonyl oxygen, either one, it's fine. It's a symmetrical compound, so either the left or right carbonyl oxygen is going to actually act as the nucleophile and attack the free proton on phosphoric acid, okay? Then, after that happens, then what's going to happen is now you have your protonated carbonyl oxygen. Then, salicylic acid is going to act as the nucleophile towards the carbonyl, and since carbonyls are commonly very electrophilic at the carbonyl carbon, the oxygen is going to act as the nucleophile and attack the carbonyl carbon. Then the electrons are going to move up from the pi bond and go up into the oxygen. Then once you're here and you have your intermediate, you still have your protonated ester in this case, and so you're going to want to actually abstract it. So what happens is the phosphorus, remember, because phosphoric turns into phosphorus acid is going to take off that proton from there to remove the extraneous proton from this. And then what happens is that going forward, you still have your alcohol here with electrons that can be donated down, because you have your intermediate of the acetic anhydride bound in. So what happens is that the electrons will move down to recreate the double bond, and then acetic acid can actually leave on its own because it's a very stable leaving group. And so finally, you're left here with your extraneous proton on your carbonyl oxygen. So then the acetate ion will go forward to take that proton from your carbonyl oxygen, and then finally leave you with your acetylsalicylic acid and your byproduct of acetic acid, which would be here. And so then, of course, like we discussed in the lab manual, we're performing the spectrophotometry and then melting point analysis. And so, of course, here's some extraneous information that you'll want to review for the sake of your knowledge and learning synthesis. You would take your acetic anhydride, and as a liquid, you would want to actually measure it out and quantify it over. You can utilize the density in order to calculate your grams. But in this case, we're going to be using milliliters. So you would pipette it into your graduate cylinder, weigh out your salicylic acid in a solid container, and then you would only have to add phosphoric acid in catalytic amounts, because this reaction is actually a cyclic reaction that regenerates the phosphoric acid, turns into phosphorus acid, then comes back when it takes that proton out, recreating phosphoric acid. So that's why you only need 5 drops. It's a very small quantity. You don't want to overdo these kind of reactions, because it can lead to a lot of side products that will be unnecessary and, you know, possibly reduce your overall yield. So we just add in our 5 drops, and then we're good to go. You take it over, fast forward through here, add in everything, heat it up. It's going, watch your temperature, and then I'm going to jump through to come over to your precipitation, followed by filtration. And I'm not going to go through these repetitive steps, because we've seen these multiple times. And if you need to know how these specific individual steps work, please make sure to watch through the video and pay close attention to the things for review. The main thing I do want to get over to is performing the spectrophotometry. So let me see if they actually have it here. Okay, so this is a pretty important part that I'd like to discuss with everyone. So salicylate, the anion itself that's unreacted in the reaction, right? So this can actually couple in an inorganic method that will bind to the iron 3 ion, the FeNO3 subunit. And so you will see it here as denoted as partially bonded to this iron hydrate complex. So what happens is that we can actually look at a spectrophotometer between the wavelengths of 400 to 700 nanometers, and you can locate the location of this tetraaquasalicate ion. And then once you have that, you would find your absorbance. Now, utilization of Beer's-Lambert law would tell us that concentration is relative to absorbance divided by the path length and molar absorptivity. And so from that, then you can back calculate and go forward in order to understand how much salicylate dianion that you have in solution or salicylic acid starting material. And you, of course, have your final product because you've weighted on the scale, but you need to remove it from it because then you would still have salicylic acid present in your product. So going forward, looks like they didn't have that. So let me just come over here for one moment and see if they possibly have the spectrophotometer. Okay, so according to this, they do. And for review, of course, you can watch through the full video, but we're going to just take it over here and jump across. We've taken our product, and then we're dissolving it down and going to prepare our iron solution. So let me kind of skip ahead because a lot of it is a lot of stirring. And so let's see here. Now we're going to be preparing our iron solution. And let me check the chat really quick. Yes, I'll send out the data. I'm not sure why the data has been locked for some people, but we are going to tackle that. However, now that we've prepared, so we have here our violet dye solution, just the coloration that is created from this iron complex. And then we're going to prepare our lab quest, which will have our spectrophotometer on it. And you would want to firstly calibrate by utilization of the iron subset. So you place it into your cuvette, and this will be your blank. They call it a blank because you need to have it as a reference point to standardize your spectrophotometer. And then so he placed it into here, and it's run through. We have a blank, everything's set now. We're going to remove it. I'm going to rinse it. And I'm going to be just kind of skipping through to mainly show you. So here, this is what we're going to do. So when you utilize this, you rinse your cuvette firstly with your solution. So that way that you make sure that what's going to be in that cuvette is going to be primarily your solution. Then, now he has his cuvette filled, okay? Make sure that the side glasses of your cuvette are nice and dry. So see, he's wiping it off with a chem wipe to make sure that it doesn't interfere with any of the analysis. Place it into there, and then by utilization of the lab quest, I do wish it was a little closer zoomed in, but you just have to click this button that says collect, and then it'll actually give you your wave numbers and your relative absorbance with your curve. It's kind of hard to see, but you can see that there's a color spectrum, and that's kind of an overlay so that way that you can see the color spectrum within that spectrophotometer graph. And so now he's taking the peak. You always want to take the peak of the given wavelength, and then you can abstract that absorbance value, which in this case, at wavelength of 577.8 nanometers, you have an absorbance of 1.226. So absorbance is equal to concentration times molar absorptivity times path length, Beer's-Lambert law. I'll pull it up here in a moment. And then you perform your abstraction of data. And so then here is the way that you would quantify it. And I recommend to watch through this portion as well. I recommend to watch both so that way that you have a good understanding of the full entire synthesis and analysis. But this will be the primary method that you're going to perform your back calculations in order to obtain your quantity. And so you take your relative moles per liter, and then the quantity that's the concentration in this substitute. So 0.1 liter over 0.01 liter in that case, because it's been diluted down, and that will make you with your equivalent moles. And then you would take the moles, multiply it by the molecular weight, and you would finally get your quantity, which is a good 22 milligrams of salicylic acid in this case. So you take your full product, you subtract your salicylic acid quantity from it, and then you're left with your final actual yield. And then you can take the quantity of your actual yield, which in this case they're saying here aspirin, over the given total quantity of sample, multiply by 100, and then you have your percentage of purity. And in this case, it was 94.6%. So again, that is the primary mathematic behind it, just to show you for a relative instance, Beer-Lambert law. So absorbance, which is A, big A, is equal to molar absorptivity, which is relative to each individual component, times the length of the light path, which is relatively 1 centimeter, and then concentration. That's the concentration of your given compound. And the molar absorptivity is going to be a specific unit for every individual compound. So every compound that you analyze has a quantifiable molar absorptivity that is a standard number, and that is going to be provided to you by the data. So now that we are at the point where we would discuss data, I'm going to open this back up and show here, and then I will be additionally be sending this data to everyone after we take a peek here just to show you. So the data here, you're going to get your mass, you're going to get your volume used, and so in this case, you're going to have to go forward and back calculate like they did it in the video of the relative liters over, so converting milliliters to liters, your weight, converting to moles, and then finally to get your total quantity of aspirin. That's a normal subtraction from your filter paper. Then through the testing of the purity, that's where you would utilize the second set of information that we just discussed on the analysis of aspirin. So if it was a little too fast of my explanation, please watch through that second video within great detail, because it will accurately show you step by step how to do it, especially that you have your given values here. You just have to utilize the calculations correctly. And then of course, this is the other page for the other students. So I'm going to download that and send it over. And then right here, the spectra. So the spectra, you need to, this time, remember, you need to analyze every functional group that changes between the two. So there are some staunch differences here between the two, and you need to make sure to analyze which specific functional groups stand out. So what changes between the salicylic acid and the aspirin, and how can we quantify that? And then go forward into the NMR spectra, and you need to localize every one of the individual carbons here. So I do see a carbonyl marked as 8. Don't worry about the carbonyl. What you need to worry about is the protons. This is a proton NMR spectra, so make sure that you can analyze where you would find the hydroxyl group, all of the aromatics, and then as well this ketones, CH3. In this case, it'd actually be ester. So this ester is CH3. And then let me go forward to download this data, and then I'm going to go ahead and send it through Canvas. So if you need to access this data and it still is locked by the time that you start up on this, please make sure to go ahead and go into Canvas. And I am sending it as we speak to all of you. Data for Asprin Lab. So from download. All right, so I just sent it out. And then now you will have your data. And then I'm going to go ahead and stop this recording.